So good morning, everyone. My name is Ben Simon. I'm a final year PhD student. It seems like a long time. I've been saying that now, over a year. Working between Nigel Brandon and Anthony Kusinak's research groups. Anthony's based in chemistry over in White City, and I'm going to be talking mainly about my last sub-project of my PhD, which is consisted of studying the liquid electrolyte side of a hybrid redox flow battery. Given I'm the first talk of the day, I'll very quickly give a background slide to save people having to talk about the many reasons why we need energy storage. So I'm simplifying the myriad problems arising from a greener energy grid, and also selling short the extent of what batteries can actually do. But this slide is basically just the simplest way of expressing why batteries are important. The intermittency problem is real. It basically says that the influx of solar and wind power generation is great, but a lot of electricity these intermittent sources generate are curtailed/wasted. Large-scale energy storage is what's needed to store this energy when it's not needed and supply it when it is. To date, pumped hydro has been the biggest installed capacity worldwide and in the UK. But by 2030, the electrochemical energy storage share is predicted to have increased by like nearly 9,000%. No, not share, but compared to what it's currently at. It's also predicted that diurnal cycling is going to be the main use of large-scale energy storage in the future. So currently there are only a few players in the commercial large-scale energy storage space, and largely the technology being used is lithium-ion based. I know we have a lot of talks later on this topic, but I'm here to promote a different kind of large-scale energy storage, which is a redox flow battery. These have a lot of benefits compared to their lithium-ion counterparts, including not having to worry so much about the thermal management of the battery. But their main advantage is their ability to decouple power and capacity. Many different redox chemistries are on offer, depending on the application. But the aim is to sort of maximize your potential gap between these redox couples, and in aqueous systems to get as close to 1.29 volts. Because if you go over that, you begin to split. You might split water. So this is an exploded diagram of a redox flow battery, and this is a system that has been around for I think 20 years over in Little Bartford. All vanadium redox flow batteries are the most studied and most common redox flow batteries that. And most commercially applicable, but the one that we're going to be talking today about is the hydromanganese system. This redox flow battery is a hybrid, meaning it flows liquid on one side and it flows gas on the other, and it uses solution-based, manganese on the liquid side and hydrogen on the gas side. And for the purposes of this talk, we're not going to talk about the hydrogen side at all, and we're going to assume that it's limit free, which is a big assumption, but it's a given the over potentials associated with the manganese, I think it's a pretty good one. Manganese is the 12th most abundant element in the Earth's crust and is therefore relatively inexpensive. It has broad redox chemistry, but we're only going to focus on the manganese 2 and manganese 3 plus oxidation states. The main problem with this couple is that in aqueous solution, manganese 3 plus undergoes a chemical parasitic reaction disproportionating to manganese 2 plus and manganese dioxide. So that's the problem, and the solution that our group found is that using a titanium additive, you can not only prevent this disproportionation up to a certain concentration or state of charge, but also the titanium appears to enable us to electrochemically reduce the manganese what is usually a sink of manganese. It enables us to reduce it back to all the way back to manganese 2+. So the colloid still forms. So like this solids still form as we charge, because the manganese 3+ does appear to disproportionate, but everything returns to manganese 2+ on the discharge. So it's great that we found this combination of redox couple, and we successfully tested it in a battery, and it works with pretty good efficiency. But we still don't fully understand the underlying speciation chemistry that's going on. So the question is, how can we take a closer look at these species without disrupting any of the the delicate and very acidic chemistry? Because we can't use RDE, because we can't dilute it, because that would drastically change the chemistry and it wouldn't be the same system. So we've started using these online methods, the first of which is UV-vis spectroscopy. And one useful thing about manganese 3+ is that it has a pretty well-defined absorption coefficient, which can use and we can use that in UV-vis. So, because when you compare it to manganese 2+, the absorption coefficient is very low in manganese 2+. So we use this experimental setup where we divert some of the electrolyte coming out of the outlet through a UV-vis spectrophotometer, and this is what it looks like in real life. And it works well, giving two clear signals at 512 nanometers and 850 nanometers. I prefer the 512 one, but Anthony prefers the 851. I don't know why that's relevant, but this appears to work well up to about 70% state of charge, at which point we see this band that's increasing on the left-hand side overwhelm and dominate the rest of the spectrum. Even once we've stopped charging it, it disproportionates in it. And we believe this to be as a result of scattering due to colloid formation, some sort of pseudo-Rayleigh scattering. It makes measuring the state of charge from the manganese 3 absorption reading completely untenable. So we thought about other ways we could inspect this couple and in real time, and use the fact that manganese 2+ has a D5 paramagnetic metal center that we can observe in an electroparamagnetic resonator. Manganese 2+ returns 6 hyperfine lines that broaden proportionally to the concentration of manganese 2+. And this is what the setup looked like. And a small port, much like the last system, like a small portion of the electrolyte was diverted continuously through a capillary through the resonator. It was quite a fiddle to get this safely into this very expensive piece of kit, and also terrifying. And so with this setup, we can observe in real time, with about sort of a 40-second delay, the concentration of manganese 2+ coming out of the cell. And these are what the unintegrated signals look like. So as you increase the state of charge, you get a lower concentration of manganese 2, so that your lines get sharper. And then as you increase the state of charge, the lines broaden, and you can measure concentration from those. So if we compare the thermodynamic calculations based on Gibbs energies with our experimental ones, we see that manganese 2 concentration declines less rapidly after the initial 20% or so, much like it does in thermodynamic calculations. And interestingly, we see in thermodynamics that this manganese 3+ concentration flatlines. And and that wasn't what we observed in the UV-vis. And that will be relevant later on when I pull the two together. And in between, so yeah, we've got our manganese 2+ concentration as we increase to 100% state of charge, and then as we decrease, the state of charge. Those are what the manganese 2+ concentration profiles look like. And in between here, we have our high frequency resistances, which I've only put in because sometimes we see some interesting features in the charge or discharge. In this case, it's in the discharge, and it sort of reflects the voltage efficiency drop in the discharge. So if we combine these two manganese concentration readings, and we know how much manganese is in the system, we can use the state of charge we're at and the concentration of manganese 2 to calculate the amount of extra manganese 2 that we have in solution, and therefore how much manganese 4 that we have. So I've used this pink line, so the manganese 2 plus concentration, to work out the manganese 4 plus concentration of extra manganese 2 plus in solution. And what this tells us is that the UV-vis measurements, as we sort of thought it might before, overestimates the concentration of manganese 3 plus there is in the system, which makes sense, as there probably are other absorbing species that exist in solution. If we want to actually know what's going on in these systems, we need to know some kinetic parameters to work out how fast these processes actually take place in real time. So while these handles on the manganese 3 plus and manganese 2 plus are helpful, speciation is still not really fully understood. So in order to understand that, we wanted to do some work out how the disproportionation works. So we charge our battery to various states of charge and then let it relax while tracking the manganese concentration and the potential. So we get these transients when the battery is just sort of relaxing. So we're able to, from the manganese transients at 100% state of charge, we're able to, we're able to basically extract 2 time constants. One that we think is associated with just the tank, with the concentration of manganese in our tank, which is helpful. And then this initial sort of hour-long period where the whole system needs to be mixed, and that's what the shorter time constant is associated with, we think. But these are pretty fresh results, so we haven't quite finished analysing them. We're still in the process of working out how to best to fit the potential transients, but using this sort of modified Nernst equation, we can back estimate the initial manganese 3 plus concentration, which, if you remember, in the thermodynamic calculations, it flatlined at about 0.3 mole of manganese 3 plus. So this actually fits quite well with our with the thermodynamic calculations, even though the fit doesn't look very good just yet. So in conclusion, we've developed 2 operando techniques to measure concentrations of manganese for analysis and diagnostics. Titanium additives are effective and prevent the manganese the manganese dioxide being a capacity sink. And there's a lot more interesting work to be done in the manganese chemistry field. I want to thank everybody that's been involved in this project, and to my funding and the rest of the Kusnet Research Group.